In the previous couple of sessions, we have seen two equations relating to mole that are very useful in chemical calculations. One of them is the Avogadro's equation that says 1 mole of every substance contains 6.022 times 10 raised to 23 particles of that substance. Whether particles are atoms, molecules, formula units, ions, depends on the context. The other equation that we also have worked with relating to mole says that 1 mole of all substances have a mass equal to the molar mass of that substance in units of grams. The third equation that is also very useful when we are dealing with moles of substances in chemical calculations, it uses the chemical formula of the compounds, and more specifically the subscripts in the chemical formula of the compound. So let's take an example of glucose. Chemical formula of glucose is C6H12O6. The elements that are present in glucose are carbon, hydrogen, and oxygen. From a previous session where we introduced the idea of chemical formulas, we said that the chemical formula tells us the elements, gives us the elements that are chemically combining to make up this compound. And we also said that for a molecular compound, the subscripts in the chemical formula give us the actual number of atoms of every element in one molecule of that compound. Now, glucose, if you notice, is a non-acidic molecular compound, which means that one molecule of glucose contains it requires 6 atoms of carbon, 12 atoms of hydrogen, and 6 atoms of oxygen to be chemically combined. In other words, let's say we had 15 molecules of glucose instead. That would have 6 times 15 atoms of carbon, 12 times 15 atoms of hydrogen, and 6 times 15 atoms of oxygen. I mean, I think you kind of get the idea. Basically, depending on one molecule, what the combination of atoms is, you can then figure out the number of atoms in X number of molecules. However, what if instead of all these numbers, random numbers, we had 6.022 times 10 raised to 23 molecules of glucose? In other words, the Avogadro's number of molecules, which would then mean that there are 6 times n carbon atoms in that sample, 12 times n hydrogen atoms in that sample, and 6 times n oxygen atoms in that sample of compound glucose. Now, if you remember, what do we call a sample that has n number of particles? In other words, Avogadro's number of particles are 6.022 times 10 raised to 23 number of particles. What do we call that? Exactly, we call that a mole. So from now on, when we talk about the chemical formula of any substance, whether it's an element or a molecular compound or an ionic compound, we need to remember that the subscripts give us the number of moles of atoms of each element in 1 mole of that compound. In other words, from now on, instead of talking in terms of atoms and all, we will talk in terms of moles of atoms or moles of ions or so on and so forth. So for glucose, therefore, 1 mole of glucose contains 6 moles of carbon atoms because of the subscript 6, contains 12 moles of hydrogen atoms because of the subscript 12, and 6 moles of oxygen atoms because of that subscript after oxygen in the chemical formula. So in other words, from now on, when you look at the chemical formula of every compound gives us the molar ratio, and please, that's the important word there, the molar ratio of elements in 1 mole of compound that has those elements. And that is why the subscripts will therefore be very, very useful in calculations involving such this idea. Okay, so from now on, please remember that whenever you look at the subscripts, we are thinking about molar ratio. So for example, let's answer these questions very, very quickly. Can you tell me how many moles of carbon are there in 1 mole of C12H22O11? Exactly, 12 moles of carbon because of the subscript 12. How about how many moles of aluminum cation, and please note that word, in 1 mole of aluminum carbonate? What do you need in order to answer this question? You need the correct chemical formula. What is the correct chemical formula for aluminum carbonate? Please, if you're having difficulty answering this question, you do need to go back and review all the problems and recordings in order to remind yourself how to do that. So aluminum carbonate, the chemical formula, of course, is Al2CO3 thrice. Therefore, there will be 2 moles of aluminum 3 plus cation in every 1 mole of aluminum carbonate. Oxygen in 1 mole of chromium 6 oxide. Once again, first step is to write the chemical formula of the compound correctly. Chromium 6 oxide is CrO3, which basically then means that there will be 3 moles of oxygen in 1 mole of the compound. Hydrogen in 1 mole of phosphoric acid. Phosphoric acid chemical formula is H3PO4. So therefore there are 3 moles of H in 1 mole of phosphoric acid. So once again, the subscripts in the chemical formula of compounds give us the number of moles of each element or ion in 1 mole of the substance. So that's the molar ratio that we get from here. And we can use this molar ratio as a conversion factor. Whenever you need to go from moles or go between moles of a compound and moles of element in that compound, then we can use the subscripts as a conversion factor. For example, here is a problem. It says calculate the number of moles of each type of atom in 2.043 moles of ethanol, and the chemical formula of ethanol is given. So basically, as I said, when you're trying to convert between moles of an element and moles of a compound, we need the subscript. So if you're trying to set this up, we start with what's given, moles of C2H6O, and then the conversion factor. Remember that the conversion factor allows you to cancel out the unit that you do not need. In this case, that's moles of C2H6O, crosses that out and converts it into the unit that you do need, in this case moles of each of the elements. So let's first convert it into moles of carbon. The ratio of this, the numbers that go in the conversion factor, the molar ratio comes from the chemical formula. The chemical formula of this compound says that 1 mole of C2H6 has 2 moles of carbon atoms. And therefore, when you complete the calculation, we get 4.086 moles of carbon. Please go ahead and pause the recording and complete the problem for the remaining elements in ethanol. Hopefully when you did that, you got the answers as 12.26 moles of hydrogen in the correct number of significant figures, and also 2.048 moles of oxygen. Please remember that at the end of each of these problems, you do have to round the answer to the correct number of significant figures based on the data given. Okay, so here's another problem, in which case, once again, notice the conversion is between moles of a compound and moles of element in that compound. So once again, subscripts will let you do that. This time, of course, we are given the moles of the element in acetic acid. So we start with 3.92 times 10 raised to minus 2 moles of oxygen. Now this time, please note, and it's very important to notice this, I did not write O2 because O2 is free oxygen, oxygen gas that exists in air, the gas that we breathe in. But in this context, the problem is not talking about oxygen gas, the free oxygen. It is instead talking about the oxygen element that chemically reacted to make acetic acid, the contribution to acetic acid that is coming from oxygen. So in this case, it is not free oxygen, it is instead O atoms, and therefore we just write O and not O2. Okay, now before you actually write down the conversion factor, which will allow you to convert moles of oxygen in acetic acid to moles of acetic acid, you need to know the chemical formula of acetic acid. So, as I've said before, if you're having trouble doing that, you have work to do. And now you need to go back and review those exercises so that you can figure it out. Acetic acid chemical formula is HC2H3O2. So HC2H3O2. And then if you see that the subscript for oxygen is 2, which means 1 mole of acetic acid will have 2 moles of oxygen atom in them. If you solve this problem, the answer comes out to be 0.0196 moles of acetic acid. Please make sure that the answer is in correct number of significant figures, and it seems like it is, so it's done. Okay, so as a review, once again, any conversion that requires you to go from between moles of a compound to moles of element in the compound, or in the other direction, in the reverse direction, we need to know the subscripts in the correct chemical formula. I mean, obviously it has to be correct, but you need to know that, because the subscript in the chemical formula give us the molar ratio of these two units.